this is a follow-up preview of the dredge logging use case for having real-time dynamic map tiles. So we are catching a position stream from MQTT broker for a cutter head dredge. It's sending a number of parameters derived from the NMEA sentences, also the heading, the kinematics, the calibration to compute the location of the cutter head as it is sensor tracked beneath the surface of the water down to the seafloor. So in this map view, we can see that there is a mining pit. This is an old satellite image, so actually the entire area is flooded, even where we see data, because this is a floating cutter head barge or dredge that is mining sand from a pit. And it needs water to do that. So the water is, in fact, up here as well. And you might notice this updating. It is able to update in real time. So now I'm going to walk you through the process. But first, let's get out of the real-time scenario. I'm going to focus the map to a workbench kit that I have running behind me so that I can actually articulate the cutter head, and we can watch the tiles being generated in real time. So in this example, the GPS is on the desk behind me, but I've shifted its coordinates to be in Mobile, Alabama. And you can see we've already done a test case there. So if I turn off the sensors, there we go. Then you'll see there is a heat map feature that expires. It acts like a comet plot. It's just there to help the eye identify when the points get a little hectic. It'll show you where you are, as well as the sensor marker, which gives you some of the metadata. So in this case, it's telling us the depth in feet. So if I articulate the sensor, as we approach our dig2 surface, the color changes in accordance with a color map that's already scaled to the bathymetry. Now I can go beyond that in this case, because this is on my desk. In a real world, that would be a catastrophic moment. But you can see what's happening on the map view is the heat map is tracing and following the marker. And we are also going to leave behind the footprint in the map tiles of where we just were. So we will have extended that tract, and it will be a color-coded stream of pixels all occupying that map tile. So I'm going to give it a few seconds to let the heat map expire from there, and you can already see that we now have new pixels in our map view here. So we've created these on the fly, and these are accessed by the standard map tile URL. So it would be a zoom x and a y.png. So that's part of the URL. We'll look at that in a moment. So if I turn off my sensors and my heat, you can see those are the map tiles. So much like we were seeing in our northern example, we'll go back to. Over time, that's going to build us a data set showing us where that dredge has reached a maximum depth for any given pixel in any given map tile in any given zoom level. So that's created on the fly. That's a dynamic and reactive process. So the tile structure for that looks just like any other map tile structure. You have a directory of tiles. And then your first level are the zoom scales, so 0 through 18 in this case. 18 gets us into a pixel size that is more fitting of our use case. We're working on scales of meters, as this cutter head is a couple of meters in size. We don't really need to go down too much further, but we could go all the way to zoom 24, in which case the size of a pixel on the map would represent about 25 centimeters. So if we look in the zoom level, then we have our x coordinates for the tiles. Then we could look into any given x coordinate, and then we would have the y coordinate. And normally this would be a PNG file, but in this case we've done something a little bit different. We're actually writing the image into a tile table, and we're tracking we're timestamping it. And we're tracking the data that creates the image. So this is the data for any pixel in the tile. Now each tile is 256 by 256 pixels. Oh, I'm going to stay here. And so we would see that here. These are the X and Y values. They're going to go from 0 to 255, so that's 256 values in both the X and Y dimensions. So these are the pixel coordinates for this map tile. And we can see, if we sort by count, that we have modified certain pixels more than others. So we've modified this pixel 111,202 33 times, and some pixels aren't modified yet, but they would be in time. And this is a nice feature because as the zoom scale becomes less focused, or as we zoom out, this is going to happen less frequently, or not less frequently necessarily, but on fewer tiles. So this happens more so the more we zoom in. So we are actually tracking the Unix timestamp, the position and depth that created the last maximum depth value for this coordinate. And now all of that, these are unique. There are only ever going to be 256 by 256 rows maximum in this table. And that will always create an image. Now every time any row is updated, the entire image needs to be updated. So we don't want to do that in real time necessarily. We can, but we'll end up with, over the life of the project, potentially thousands of map tiles representing tiles where only one pixel was updated. So we can downsample that in real time too. So we're only going to look at tiles every hour. So if I look in my tiles table, then here we have the epoch or the Unix time in hourly intervals. So every 3,600 seconds, we're going to create a new blob, which is just the binary representation of the image. So now when we access our map tiles with our tile server, it's actually going to be translated into a database query to get one of these images. Now these are being created and modified in real time, but we're not limited to the most current. We can now go back and mine a map tile for a older portion of the survey, or we could stay with real time, which would be giving me the most recent map tile. And this is very nice because the map tile directory structure allows our unique databases at each tile to be written to and read from with a much higher efficiency than doing all of this in a single database. So concurrency is no longer a primary concern. And we also have the time series of the tiles and also of the vector data. So we can reaggregate and we can do any number of things. But also the reaggregation has actually already occurred in real time because our data logging process was a multi-threaded process wherein at any given zoom level runs in its own thread. So any given zoom level has its own database for every tile at that zoom level. And only the tiles that are on screen are going to be accessed, even though any tile that needs to be written to and updated is. So here now is a quick walkthrough of the code there. So this is the actual code that receives the MQTT messages. Whenever it receives a message, it decodes it, parses it, it gets the data in our database example, it gets the Unix time, the depth. EPSG code is not used at this time, but it is useful to have it. This is where we do our kinematic calculations are all done in a Cartesian system and not a geographic system. And that's where that has relevance. But we're also getting the geographic position, and our initial counter is 1, and it'll be updated as needed. So for every message we get, or every row in our database, we're going to pass that off to our tile database routine. So as I was saying, this was multi-threaded. For every zoom level, it's going to create a new thread, and it's going to use a thread pool. So it's going to reuse those threads for efficiency. But basically, all it needs to do is take the input parameters, use those latitude and longitude coordinates to convert to both tile coordinates and pixel within a tile, so the pixel coordinates as well. So the physical address of the database is the zoom scale and the tile coordinates. And then the data within that database are the pixel coordinates and the data and the imagery. So if we go up to the next call would be to update the table. We're passing that same information. However, we're giving it our pixel coordinates as well. And so the first thing it does is it checks the existing database, the actual data table, not the image. And it looks for the particular bin that this data coordinate represents. If the depth that we have from our latest stream of messages is deeper than what's in there, then we're going to have to update it. If it's not in there at all, then we're going to have to create it. So in the result, that's what we're doing here. If the new depth that we've just received is deeper than the one in the database, then go ahead and replace it. If it doesn't exist, then go ahead and insert it. The difference between these two would be the counter. If it exists, we're going to update the counter. And in either of those cases, that's going to trigger the need to recreate our map tile. And so we're going to do that as well, but we're going to timestamp it with the timestamp rounded to the nearest, or floored rather, to the nearest hour. And that will prevent us from writing thousands of map tiles into our tiles table. We will only be writing in every hour, or so we're basically replacing everything up to the end of that hour. And now we can serve those up. So what happens is when a client sends a URL through a web browser or otherwise, they're going to send a tile URL, which is going to have something more like this. It's going to have the host name, the port we're serving it on, the path to the tiles archive, and then it's going to have these templates for the zoom scale, the X tile coordinate, and the Y tile coordinate, and it will be in a PNG format. However, we know that they're not actually stored in PNG formats. We're actually storing them as databases. So what this does is it intercepts the URL. It matches the path for the zoom, the X, and the Y coordinate. And it says, send those up to the maptile server. So if we click on this, we can see that with a location of the tile archives, the zoom and the XY, we're now into this function, which is immediately going to request the tile from that database with those same parameters. And it's going to feed that binary blob directly back to the web browser. So it's about as fast as just sending an image file direct. And then here's the actual access. So it's just a query. If we have a given tile path, a zoom X and Y is going to convert the PNG to database request. It's going to send the query in to get the image from the tile. We could pass the timestamp in here as well, but right now I'm just saying give me the most recent. So give me only one tile. Send it all the way back through to the client. And that's what led us to this result. So there you have it. We have a way of storing a massive point cloud as a sparse matrix of map tiles in the form of databases. And we can do that over time. So it is sparse in both space and time. However, to the client, it would appear as though it's a full matrix data set.